Section 4.5 is on page 285, talks about derivatives of logarithmic functions. Derivative of a natural log of x is simply 1 over x. And if u is differentiable function of x, derivative of natural log of u is 1 over u times the derivative of u with respect to x. This is again using the chain rule. Now, something that we came across was the change of base formula. That's extremely important. We're going to be using that here in this section. So if I see a log and the base is not a 10 or an e, I could write that as log of the argument divided by the log of the base. So we want to practice a bit of derivatives. Now notice logs have a lot of properties. So here I could say, if I want, f prime equal 1 over whatever the argument is times the derivative of the argument, which is 7. So f prime would be 1 over x. Or I could say f of x is natural log of 7 plus natural log of x. Properties of logs. This is the third property or law. When I take a derivative, that's a 0 plus 1 over x, which is 1 over x. Either or, it doesn't really matter. It saves you a lot of work if you use the properties of logs. You don't have to, but then you're doing the problems the long way, or the brute force, however you want to see it. For number 6, for example, if I could write this as natural log of 1 minus 2x raised to the 1/5, then I know by the third law of logs, I could move that up front and say y is 1 over 5, the natural log of 1 minus 2x. And now when I take a derivative with respect to x, 1/5 I ignore. Derivative of a log is 1 over the argument times the derivative of the argument, which is a negative 2. So this turns out to be negative 2 divided by 5 into 1 minus 2x. Again, that saves you a lot of work if you could use those properties. Again, the log of a product is the log of the sum, if you recall. And if you need a quick review of those, we did those back in section 4.4, and you could kind of review them right there. So this would be natural log of x plus natural log of 2x plus 3 to the 2nd power. I could even clean that further and move the 2 up front by the third law of logs or property, depending on which author you're talking about. And the derivative of this would be 1 over x plus 2 times derivative of a log is 1 over the argument times the derivative of the argument. Now, if I'm only asking for a derivative, you really don't need to combine those. You could leave the answer like this, that's fine. And here again, I could say f of x is natural log of 1 plus e to the x minus, because you're dividing, if you recall, and f prime would be (1 over 1 plus e to the x times the derivative of this, which is e to the x, minus 1 over 1 minus e to the x times the derivative of that, which is negative e to the x. So f prime is e to the x over 1 plus e to the x plus e to the x over 1 minus e to the x. Again, on a test, I'll accept that as an answer. For the homework, you need to get a common denominator. So you multiply this by 1 minus e to the x, you multiply this by 1 plus e to the x, and you'll notice that you'll get factor e to the x out, that's 1 minus e to the x plus 1 plus e to the x all over 1. These are conjugates. 1 minus e to the 2x and that would be e to the x times, those will cancel out, a 2 over 1 minus e to the 2x. Again, on a test this is sufficient. Now, a quick reminder, if I take a log, if I could match the base of the log and the base of the exponential, they undo each other, so to speak, if you recall. And if I write this as log base 6 of 1 over 6 squared, move this up, those undo each other and you're left with a -2. Similarly, I could write this as a log base 8. 512 is 8 cubed. Those will kind of undo each other and you're left with a 3. So, these properties are going to come up now. You're going to use them a bit. And the change of base formula is a must. I could say this is natural log of 10 divided by natural log of 6. I'll plug this in my calculator, and they didn't specify. We're going to take 3 decimals. Let me get my calculator out. If I take natural log of 10 divided by natural log of 6, and that would be 1.285. 1.285. So if they don't specify, 3 decimals will do. Here again, I don't have a base 5 in my calculator, so this is natural log of 12 over natural log of 5. By the way, I could have used log of 10 divided by log of 6 with a base of 10. It doesn't matter, you get the same answer. And just for practice, if I take my calculator, instead of natural log, if I use the log of 12, this is a base 10 because the change of base formula does not specify. You could use any base you want. We're using the base that match or need, 1.544. 1.544. And if I get to number 34, the same deal, I'll say that's natural log of 2. I like natural log because it's only 2 letters instead of log 3 letters. Oops, 2 nines. So log of the argument, whatever the argument is, divided by log of the base. And if you plug this in your calculator, we need to round that to 3 decimal places. And that would be natural log of 2 nines divided by natural log of 7. And we get a negative 0.773. Negative 0.773. Now, when I get to the calculus part, this is number 74. It says demand. And 73 and 74, find the XDP. X is the number of, P is the price in dollars. That's what demand is. And X is the number of units. 40, 80, 120. So if I take a derivative of this, the derivative of X with respect to P, that would be the quotient rule. Derivative of the top is a 0 times the denominator minus the top times derivative of the denominator, which is 1 over p squared plus 1 by the chain rule times 2p. So dx, all over the bottom squared, almost forgot. So dx dp would be the top, that's a 0, that is, okay, I need a bit more space, let me get that going. And if I shift this a bit down, a lot of space, that will be negative 1000 p divided by p squared plus 1 divided by natural log of p squared plus 1 squared. Now, since they told us interpret the rate of change for a price of $10, at a price of $10, this would be, and again, I could just plug this in my calculator and figure out what this number is. I could write it exactly as I see it. So I'll take a negative 1,000, p is 10, divided by p squared 10, too many, there we go, 10 squared plus 1, and I could right away say divide by parentheses natural log of p squared 10 squared plus 1 close parentheses and square the denominator, and I'll get a negative 4.65. I'll get a negative 4.65. The units x would be the dollars, and oh, I'm sorry, and p is, I got it backwards, didn't I? That is, x is the number of units per dollar. Okay. And this indicates when the price, or at a price, of $10, the demand is decreasing at a rate of $4.65 units at that time. 4.65 units. Number 78 is next. So here they give us the cost function. The cost is given by this equation with the cost of producing X units. Okay. A, find the average. Well, that's simple. The average is the cost divided by X. The cost is 100 plus 25X minus 120 natural log of X all over X. The cost function would be $100 over X plus 25 minus 120 natural log of X over X. So, if I take part A, that's my equation. I could write that slightly different if I want to take a derivative. Instead of using the quotient rule, I could write it slightly different. So I could say the cost function is actually 100x to the negative 1 plus 25 minus 120x to the negative 1 times natural log of x. This way I could avoid the quotient rule. So part B, take a minimum. How do you find the minimum? Analytically means by hand. Take a derivative, set it equal to 0 where it's undefined. Bring the power down, subtract 1 from the power. Derivative of 25 is 0. Minus 120, I'm going to leave it alone. Product rule. Derivative of the first times the second plus the first times derivative of the second. So the cost function is negative 100 over x squared plus 120 natural log of x over x squared minus 120, and when you move that down, x times x is x squared. So here it is. The cost function prime is all over x squared. That would be negative 220 plus 120 natural log of x. Now to find the critical numbers, where does my derivative equal 0? Where does my derivative not exist? Well, the not exist part is when the denominator equals 0. That's not even allowed. But where does the top equal 0? Negative 220 plus 120 natural log of x equals 0. That is when 120 natural log of x equals 220. Natural log of x equals 220 divided by 120, which is, again, I'll use my calculator. If I take 220 divided by 120, the zeros cancel out, of course. 22, that's 11 over 6. So basically, x will be e to the 11 over 6. Now my testing, that's fairly simple. Since 11 over 6 is a number that is bigger than 1, if I take e to the 1 as a test point, right, that's less than that, because this is bigger than 1. If you put, the denominator is always positive. If you put an e to the 1 right there, that will become a 1. 120 minus 220 is negative. And if I take a number to the right, well, e squared is to the right of that, right? Because that's 1.7, this is 2. E squared right there, natural log of e squared is 2, times 120 is 240, minus 220 is positive. The function is increasing. What does that mean? Find the minimum average cost. We have a minimum average cost of, and I get my calculator. The average cost function is right there on the right. It's going to be, so I need e raised to my answer. There it is. 6.25, $6.25. I'm mixing things up. C was the number of units, wasn't it? The product cost of producing X units, 6.25 units roughly. So what is the average cost for that? If I go by my calculator and I take now the cost function, which is in green on the right in part A, that's 100 divided by my answer plus 25 minus 120 times natural log of my answer divided by answer. 5.8. I need some space. Okay, that's okay. The average cost of $5.8. Find the minimum cost. There it is. When we produce roughly 6.25 units. And there's our homework. Number 77, you're going to do parts A and B. Not sure why it says B. Parts A and B only.